than the rest of them, obviously that's going to take that concept average, so that's going to change the overall average. So you do have plenty of time until next Wednesday to get those done. And of course, you can do them up to 5 times so you can make the best grade possible. So there isn't a reason why you can't make a high A on that concept check average if you just go through and do those. So that's where it's at right now. So obviously, if you do better on the concept checks, that grade will go up, and that will help your overall. If you do worse or you skip them and you just don't do them, then that concept average is going to go down, and that's going to change the overall. So I just placed that in there so you can kind of see what it does to your grade and how does it set you, so you can make those informed decisions for the rest of the semester. Okay, so it's tentative; it can change obviously as those grades change. So starting with our brain and cranial nerves. So research suggests that about half of our genes are expressed in our brain because it's kind of like a big deal, kind of important. This is compared to plants. With plants, half of their genes are expressed in their flowers. So they're more concerned with looking pretty and making babies than we're just here thinking about stuff. Probably why we're higher up on the food chain in the plant life. So when we look at the brain, in the beginning, when you look at vertebrate brains, whether it's a fish or a lizard or us, it all starts off the same thing as this long dorsal tubular nerve cord. And at a certain point in development, the end of that nerve cord is going to enlarge to become a brain that's known as encephalization. So it just looks like you blow a bubble on the end. And of course, that bubble is going to become the brain, and the rest of it stays the spinal cord. Then as we continue to develop, that single bubble divides into 3. And that's going to be the forebrain, the midbrain, and the hindbrain, the prosencephalon, the mesencephalon, and the rhombencephalon. As we continue to develop, those bubbles are going to further subdivide. So we'll end up with 5 little bubbles that will become the brain. The very first bubble is known as the telencephalon. So you remember telencephalon top, it's the first one. That's going to become the cerebrum. So for us, it's going to be a very big deal for the brain. The second bubble is the diencephalon. Di means 2, so that's our second bubble. It's going to become the it's going to become the thalamus, the hypothalamus, and some other little structures. The mesencephalon becomes the mesencephalon. That becomes the mesencephalon. Apparently, it decided, I'm not changing my name for you people. Mesencephalon is just Latin for midbrain. Okay, so that it doesn't change its name regardless of the development. And there's several structures of the mesencephalon. And then the last little hindbrain bubble divides into 2. We're going to make the metencephalon, so that's going to become the cerebellum and the pons, which is why these 2 areas can communicate quite frequently with each other because they come from the same part back in the day. And then the very last little bit is going to become the myelencephalon. That's going to become the medulla oblongata. So that one's showing you roughly 5 weeks of development. And then by the time we get to the adult brain, we can see the telencephalon becomes the majority of our brain. Then the diencephalon, and then the mesencephalon, that becomes the mesencephalon. The metencephalon and the myelencephalon, so those different regions. Now, one of those characteristics of being a vertebrate is having that what is known as a dorsal tubular nerve cord. It means it has a hollow in the middle of it. In the spinal cord, that hollow is the central canal filled with CSF. In the brain, those hollow chambers are called ventricles. And the ventricles flow into each other. They are continuous from one space to the next to the next. It's kind of like a shotgun house. So if you are from the South or Appalachia area, they have what they call shotgun houses. And it was a very easy way to build houses that used minimal amount of building material. And they were called shotgun houses because the living room, if you walk into the front door into the living room, there would be a little archway into the dining room and then an archway into the kitchen and then the back door. So the theory was you could stand at the front door and shoot a shotgun into the house and the bullet wouldn't hit any walls. It would just go through the openings between. Because apparently that's what they used to do a lot in Appalachia, was shooting at people's houses. Crazy rednecks, okay? And of course, later when they came up with duplexes, they were called double barrel shotgun houses because of the way the doors lined up. It made it very efficient on building. That's kind of how these are. So just like the living room could flow into the dining room, that flows into the kitchen, that goes out, you have one ventricle, one space that flows into the next, that flows into the next, that flows into the next. And of course, these spaces are lined in those ependable cells, lining the ventricles, lining the central canal, the spinal cord, and they are filled with CSF, so they're constantly flowing that CSF from one part of the brain to the next, and then out. So we start with our lateral ventricles. The lateral ventricles are the ones on the side. They're going to be in the cerebrum. So technically it'd be ventricle 1 and ventricle 2, but nobody can decide if the right one is number 1 or if the left one is number 1. So we just call them lateral ventricles. They're going to be separated from each other by a fleshy piece of material called the septum placidum. Again, septum meaning to separate, like your nasal septum separates your nose holes, and placidum, which means pale colored tissue. Okay, so it's just this kind of pale colored tissue separating the two from each other. From the lateral ventricles, we're going to go through an opening called the interventricular foramen. Sometimes you'll see it called the foramen of Monro, so M-O-N-R-O. That's the guy that found it. So that interventricular foramen will then empty the CSF from the lateral ventricles into the third ventricle. Now, the third ventricle surrounds the thalamus. So you can remember third ventricle, thalamus, the THs kind of hang out together. From the third ventricle, we're going to flow through a short chamber called the mesencephalic aqueduct. It's also called the cerebral aqueduct or the aqueduct of Sylvius. So mesencephalic aqueduct because it's found in the mesencephalon, the midbrain. Cerebral aqueduct because it's draining stuff from the fourth ventricle is right around the medulla oblongata. From there, we're going to flow through an opening called the foramen of Lucia, which we'll talk about. So here we have the flow. So our lateral ventricles through the interventricular foramen to the third ventricle, through the cerebral aqueduct to the fourth ventricle, through the foramen of Lucia into the central canal, the spinal cord. Okay. Our different areas of the brain, we've got the cerebrum and all the different landmarks of the cerebrum. So that's what we'll be getting into tomorrow. We're going to have the cerebellum. We're going to have the diencephalons, which are uber important for functionality. Also by the diencephalons, we're going to have the infundibulum pituitary gland, and then we're going to have the brainstem. So as we go through the different parts of the brain, we're going to start at the bottom of the brainstem and work our way up to the higher centers. Now, before we get to the different parts of the brain, we got to talk about protection because the brain is very important, yet it's very squishy. So we want to make sure that it is protected. So we're going to have 4 levels of protection. 3 of them are physical. They are anatomical. You can poke it with a stick. You can touch it with your fingers. And the last one is a functional protection. So our first layer of protection is the obvious one. It's the skull. So the big hard bones that help protect your squishy brain. We're not going to talk about the parts because we've already talked about skull parts back on, test 2 back in the day. Then we have our meninges. So here we still have a physical barrier we can point to, but obviously being a membrane, it's going to be thinner. It's going to be flappier than your skull. And of course, we have 3 different layers. We have the dura mater, the arachnoid matter, and the pia mater. So some of these should look vaguely familiar because they were just on our last test. I know we're trying to forget, but it should be familiar from that area. So our dura mater, again, the toughest, the strongest layer of the meninges. Now, around the brain is actually a double layer. That kind of indicates how much more important the brain is than the spinal cord. The spinal cord just has 1 layer of the dura, where your brain has 2 layers. So the outermost layer is the peristeel layer. The peristeel layer is going to adhere to the periosteum of the skull bones. That's why it's called peristeel layer, because it fuses to that periosteum. It's going to help anchor everybody in place. The meningeal layer is going to form the external layer. It is the one that is continuous with the dura mater of the spinal cord. So the spinal cord only has the meningeal layer associated with it. So it's going to wrap around the brain, continue out the foramen magnum to become the outer layer around the spinal cord. Now, in between these 2 layers, we have what we call the dural sinuses. So the peristeel layer and the meningeal layer are not fused together wholly. There are little spaces, little gaps in between. These gaps are called the dural sinuses, and we've got different ones. We've got the superior sagittal, inferior sagittal, transverse sinuses. These sinuses are going to collect blood leaving the brain. Okay, so we're going to have this major exit port, kind of like having a bunch of your sewer lines go into one main sewer that goes out to the street. That's to make sure there's no backup in the system, because with the venous system, since it is so low flow, sometimes you can have a backup. And if we have a backup in the brain, that can cause swelling of the brain, and that can be fatal. So we don't want that to happen. So we're going to have large exit ports for the blood draining away from the brain itself. So that's where those durosinuses are going to come into play. This is also where we're going to dump the CSF when we're recycling it. So we have plenty of time to put that in and mix it up on the way out. Now, all of these are going to funnel to join to form the internal jugular veins as they start to leave the skull. So they will become a part of the venous system. The arachnoid matter, so separating the dura matter and the arachnoid matter is the subdural space, excuse me. The subdural space doesn't have anything in it. It's kind of like the space between your shirt and your tummy. There's just air there. Okay, there's nothing really going on. So same thing there. Usually they're collapsed and nothing is going to be sitting inside of that cavity, that space. The subarachnoid space is between the arachnoid matter and the pia mater, and as we learned, the subarachnoid space is going to have CSF, cerebrospinal fluid, and this is going to help float the brain, float the spinal cord within their cavities, whether it's the cranial cavity or the vertebral cavity. Now, unfortunately, we also have some pretty big blood vessels sitting around in there. Our body sometimes isn't built too well. You would think you would want to protect the squishy bits, but apparently, our body's not compared. These large vessels just sit in this cavity, just sit in this space. Now, they are surrounded by CSF, so that does provide a little bit of liquid cushioning, but there's not a lot of bony structures and not a lot of hard, firm protections. So unfortunately, these blood vessels can get damaged, and if they get damaged, they tend to leak. Now, because there's CSF in this space, CSF and blood don't readily mix together without proper filtering. So you'll actually have that blood soak up into the subdural space, causing subdural hematomas. So we will watch a video in lab probably on Wednesday, and it shows a subdural hematoma and the repairing of a subdural hematoma. So you can see what one of those would look like on a patient. Now, CSF is constantly being produced and constantly being reabsorbed into the body. Where we reabsorb it is areas called the arachnoid villi. Now, sometimes you'll see arachnoid villi, sometimes you'll see arachnoid granulation. The arachnoid villi are the actual structures that are soaking up the fluid, kind of like the straw in your lid. And the arachnoid granulation is the patch that has the villi. Just like the straw, we associate with the lid of your cup. Okay, so the straw doesn't go anywhere other than the lid. So you can say, oh, I'm going to drink my liquid from the lid of my cup or from the straw of my cup. It's the same area. One is the actual sucking structure. One is just the lid component. That's what the villi are. The villi are the straws, and the arachnoid granulation are the patches where the straws are located. So sometimes you'll see them use those interchangeably. So they're going to suck up that fluid, that CSF, and dump it into those dural sinuses, the superior, inferior sagittal sinus. By dumping that fluid into this big space, it can thoroughly mix with the blood as it's leaving the skull. Kind of like flushing a toilet. It's going to swirly around in there and mix everything back into the bloodstream so they don't separate from each other. The pia mater, again, like saran wrap, is going to tightly cling to all the nooks and crannies of the brain and spinal cord, and it's held in place by astrocytes.